Assalamualaikum dan apa khabar semua? Selamat datang ke channel saya, Cikgu Hasnita. Hello everyone, this is physics class Electromagnetism with the first subtopic, magnetic effects on a current carrying conductor. To begin our lesson today, let's take a look at this diagram. What does it show? Yes, it shows a bar magnet. What is a magnet? A magnet is a material which exerts a magnetic force in the region surrounding them, and the region where the magnetic force acts is referred to as a magnetic field. This magnetic field can be visualized by using iron needles or filings, and this magnetic force varies from one place to another, both in magnitude and direction. Okay, now let's take a look at this diagram. It shows how a magnetic field is characterized by field lines that can be plotted by moving a small compass inside the field. And the direction of these field lines is from the north to the south. Okay, so this is the plotting compass we place at this edge, where N shows the north polarity of the bar magnet and S shows the south polarity of the magnet. So when I move this pointer, you may observe in which direction the plotting compass moved to. Alright, so from here we can see that the magnetic field direction is from the north to the south. So from the first two diagrams, we can say that the magnetic field lines indicate the direction of the magnetic force, and the density of the line represents the magnitude of the force. So these are the characteristics of the magnetic field lines, in which the direction of this field line is from the north to the south. There is no two lines intersect each other, and the lines are continuously throughout the body of the magnet. The forces are stronger at the poles of the magnet, and the field lines can easily pass through iron rather than in air. Okay, we have seen that how the magnetic field which produced by the permanent magnet looks like. And in this diagram, let's take a look what will be the magnetic field pattern due to current. When a current passes through a conductor, it produces a magnetic field around that conductor. For example, this is a straight wire which is a current carrying conductor. It is connected to a cell, and the red arrow shows the direction of current flow in the conductor. As you can see on the white paper, it shows the magnetic field pattern of the conductor is in a concentric circles. Okay, as in the permanent magnet, the magnetic field around a current-carrying conductor can also be observed by using a compass or iron filings. For example, in this diagram, we place a plotting compass at this position, and later the magnetic needle in the compass will point in the direction of the magnetic field. On a compass needle, the red color represents the North Pole and the blue color represents the South Pole. So let's observe what happened to the pointer of the compass when I move this slider. So from this pattern of magnetic field shown on this straight wire, there are a few things we can say about the characteristic of the magnetic field. First, the magnetic field line forms a concentric circle around the conductor. And as you can see that the lines are closer near the wire, it shows the field is stronger. And as the current increases, the strength of the magnetic field will increase proportionally. And this magnetic field direction, there are changes according to the changing in direction of the current. So what are the methods we can use to determine the direction of magnetic field of this current carrying conductor? Yes, right hand grip rule is a method which we can use to determine the direction of magnetic field in a current carrying conductor. So how to apply this rule? The thumb shows the direction of the current while the focal finger shows the direction of the magnetic field line. In this example, we fix the cell in this direction, which means currents flow out of the paper. So our thumb should pointing upwards, and you can see now the forefinger curl in anti-clockwise rotation. So the direction of the magnetic field is anti-clockwise. And if we reverse the direction of current, the direction of magnetic field will also changes. For example, now current flow into the paper, so our thumb should be pointing downwards, in which the focal finger is now curled following the clockwise rotation. Other than right hand grip rule, there is another method which we can use to determine the direction of the magnetic field in a straight wire or in a current carrying conductor. It is called as the corkscrew rule, or also known as Maxwell's screw rule. So if you look at this diagram, it shows when the sharp end of the corkscrew is pointing in the direction of the current, the direction of rotation of the corkscrew is the same as the magnetic field lines. While this is another type of current carrying conductor which we call as a loop or a coil. And to analyze the magnetic field of this coil, we can use magnetic compass. A few sets of magnetic compass placed in a different position as shown in this diagram. And this is how the current flow in the loop. On the left side, we say current flow out, and on the right side, the current flow into the paper. So how to analyze the pattern of the magnetic field? Let's take a look at this animation when I move this slider. Okay, so you can see the red pointer will point to the direction of the magnetic field of the coil. In this side, the magnetic field line follows the anti-clockwise rotation, while on the right side, the magnetic field line follows the clockwise rotation. Where the field lines at the center are straight and are at right angles to the plane of the coil. And this is the third type of current carrying conductor. It is called as a solenoid. So what is a solenoid? Solenoid is a long coil with multiple turns. And how to determine the direction of magnetic field for this solenoid? So this is how we apply the right hand grip rule in order to determine the direction of magnetic field in a solenoid, where the curled finger point in the direction of the current and the thumb point to the north pole of the coil. And for this solenoid, the magnetic field strength are depend on the number of turns of the coil, the amount of current flowing through the coil, and the type of core material. So all these current carrying conductor, a straight wire, a coil, and a solenoid are called as an electromagnet. What is an electromagnet? Electromagnet is a temporary magnet where the conductor becomes a magnet when there is a current flows through them. And when the current stops flowing, so they will lose the magnetism. Okay, now let's take a look at the applications of electromagnets. Electromagnets are used widely in electrical circuit or electrical devices. Number 1, it is used in a magnetic relay. What is a magnetic relay? Magnetic relay is an electrically operated switch that enables a low power circuit to control a high power circuit. Let's take a closer look on how this magnetic relay works. You may observe the way it closes the control circuit as I switch on the control switch or the primary circuit. So the moment the switch is on, current starts flowing through the coil. And this core will be magnetized and attract the armature, which is made of metal. So this part will be lift and close the contact at the control switch. So by this, current flow in the control circuit and switch on the main power, which connected to the load or electrical devices here. Okay, let us revise again how the magnetic relay works. When the switch is on, the flowing current energizes the electromagnet, and this will cause the armature attracted towards the electromagnet. And once this happens, the movement of the armature will close the control circuit. Second application is a circuit breaker. A circuit breaker is an automatic switch that cuts off the current in a circuit if the current rises above a specific value to protect the circuit from damage due to overload. And to understand how this circuit breaker works, let's take a look at this diagram. When the current flowing through the electromagnet increases, the field strength also increases. So the increasing in the magnetic field will pull the armature and causes a break of the current flow at this part. So by this, current is stopped flowing in the circuit. And this circuit breaker can be reset by pushing on the reset button. Although a circuit breaker can protect the circuit from burnout, the practicing of overloading is best to be avoided. Okay, let's take a look at another application of electromagnet, a telephone receiver. In a telephone receiver, an electromagnet with a varying current causes a magnetic diaphragm to vibrate and produces sound. How is this happen? The sound wave from the microphone are converted into a varying current and it passes through the electromagnet in the receiver. The varying magnetic field causes the iron diaphragm to vibrate and produces the sound. And the next application of electromagnet can be found in a scrapyard cranes. A scrapyard crane uses an electromagnet to pick up and move iron debris. In these scrapyard cranes, an electromagnet consists of a circular soft iron core and windings made of insulated copper wire. Both the north and south pole are available on the same surface, which produces stronger magnetic field. So I guess that's all for today. And as usual, before we end this session, let us do the checking, the knowledge which you should achieve after following my lesson. Number 1. A current carrying conductor produces a magnetic field around it. Second, a current carrying solenoid is called an electromagnet and it produces a magnetic field similar to that of a bar magnet. Number 3. The strength of the magnetic field in electromagnets increases with an increase in the magnitude of the current and the number of turns of the coil. It is also depends on the nature of the core material. And last but not least, electromagnets are used in many applications such as magnetic relays and circuit breakers. So see you again in the next lesson. Till then, Assalamualaikum and thank you for watching. Bye!